My name is John Boutran.
I'm Jimena Plugue.
I'm Roxana Riani.
We are the Global Design Team. I'd like to thank our faculty advisor, Dr. Benjamin Basil, as well as our founder, Mr. Duriel Taylor, who is the founder of the Global company. Global means glowing while mobile. So at the start of the semester, we decided and embarked upon a mission to develop a self-powered illuminating bicycle, which had the ultimate goal of increasing rider safety through visibility, especially at nighttime. We came up with 4 specific design criteria, which were to have a lightweight frame, a self-generated illumination of the frame, cost effectiveness, as well as it should be safe and suitable for all types of weather conditions. The reason why we decided to embark upon this was that if you look at this map of the UK, the red dots symbolize accidents, where the blue dots symbolize fatalities of riders, of cyclists in accidents. In the United States, there was approximately 38,000 cyclist fatalities in 2011, which averaged out to about 13 people per week. As well as in the UK, there was 19,000. And in the EU, there was 49 people on average per week. This gave an average of 57% of accidents where the driver failed to look properly. Because the drivers failed to look properly, our goal was further enhanced that visibility was key to increasing rider safety. Therefore, we tried several prototypes. The first prototype was to manufacture the entire frame. The second prototype was to create a design with slits in the frame, as you can see from this photo. I have LEDs lighting that frame, as well as prototype 3, where we have a half-moon bike frame, where the bike would be cut in half and clear at the bottom, where LEDs would shine through that clear portion.
So this is a simple, small picture of our actual prototype, and then this is an outline of, we're going to go and break down all the different components of our actual prototype, with the first thing being the actual illumination of the bike. So 2 of the things that we explored in terms of the illumination would be the LEDs and electroluminescent components. So the main electroluminescent components that we were aware of were EL panels, EL wire. We like them because they're cool to the touch, they're lightweight, they have a Lambertian reflectance, which means it's a uniform luminance throughout, no matter what angle you look at it. There's no catastrophic failure. It continues to operate even if it's punctured or if it's nicked a little bit, and it's a low power consumption compared to LEDs, which can have an uneven illumination, and the wiring and mounting on them with our previous concepts that we were thinking about would be very complicated, as well as the thermal management that needs to be considered, such as heat sinking them, because they do get very hot. They don't emit heat, but they do draw in heat, so that's another thing that we have to consider about in terms of safety. So we actually really liked the EL component, and then we found out about electroluminescent paint, which is this, the process of applying it was patented by Darkside Scientific. The paint is called Luminor. And this was our initial design, or our final design, I'm sorry. We actually wanted it to be the whole bike painted, but in order to reduce the cost and keep with the cost effectiveness, we decided to give it kind of a Tron-inspired look, because we feel like that was enough, that if you saw this, it's an iconic shape that you know that is a bicycle. So you don't need to necessarily overdo it and paint the whole entire bicycle with the paint. So this would be the main illumination, and you have the seat stays, which would be illuminated for turn signals and brake lights. So this is our 3D CAD model, and this is our actual prototype, which looks basically just like our CAD model, which we're very excited about. And we also wanted it to look like a regular bike when it was turned off. We didn't want it to seem very obvious, which is what we were able to accomplish, at least with the main frame. The Darkside Scientific told us that if we painted over with a top coat on the red, it would drastically reduce the brightness, so that's why the red, unfortunately, was not able to be painted over. But at nighttime, this is what it looks like, and again, this will be for the turn signals and the brake lights. So again, prototype initial and our final prototype, very much similar. We're very happy with that. The luminar, the spec given from Darkside Scientific was about 0.7 milliamps per square inch, and the surface area for our actual bike was about 140 square inches, so we were expecting 98 milliamps of a current draw. So the next thing we're going to go over is the energy generation, which will be done by Roxana and John.
So energy generation is one of the most integral components of this design because we were striving to have a self-powered lighting system for the frame. So we integrated this hub generator in the front wheel of the bicycle. You can see it here, and also you can see it on an actual bicycle right here. And what it does is, as the cyclist is riding, it captures the mechanical energy generated from wheel rotation. This particular model is called a Sun Deluxe Dynahub, and it's rated for an output of 6 volts and 3 watts. But you'll see with some of our testing data that it actually outputs on average, depending on the speed, like 10 volts, and it can even peak at 16 volts, which worked great for our design. So this is the actual circuit that, I'm gonna walk you through the design process of these circuits because we had a lot of challenges. This is the actual mainframe lighting circuit that we used, and so the mainframe is gonna be powered directly from the hub generator. And the figure on the bottom left is a little PCB we made with some of these components. So component number 1 is the hub generator. It generates alternating current at about 1 kilohertz. And then that is fed into a bridge rectifier, which is component number 2, which, I'm sorry, I don't have the laser pointer, but it's this component right here.
There's a laser.
Nope, this is not.
It's okay.
Yes,
So,
it's on that.
It's on this?
Should be.
so component number 2 is a bridge rectifier. It converts our alternating current to DC current. Component number 3 is a 1,000 microfarad capacitor. It's not used to store charge necessarily, but it levels out those voltage peaks so you don't get any flickering in the frame. And component number 4 is we simplified just with an inverter symbol. Those are the inverter boxes provided by Darkside Scientific with the prototype. They're wired in parallel and they convert that DC current back to the alternating current that's required by the electroluminescent paint. So this circuit has some pros and cons. It reliably lights the frame when the wheel's spinning. And it's a compact design because we don't need any batteries. That's the whole point, to have a self-powered system. But there are cons, and some big cons that we try to mitigate. And that's that the light goes out when the wheel stops spinning and the brightness is inconsistent. The brightness of the paint is voltage dependent, and the voltage is dependent on the RPMs of the wheel.
So at this point, what we decided to do was to conduct some testing as to the performance of the hub generator. Here you see there's a graph of several trials where we correlated the voltage output of the hub generator after it came through the bridge rectifier and capacitor circuit to the RPM. This graph clearly shows that on average we have a 1:10 ratio between the RPM and the voltage, which means that, for example, if you need a voltage of 10 volts, the bike has to be going at about 100 RPM. This is particularly useful as it is a great predictor of performance as to how the circuit will behave.
So we wanted to have, say you're at a stoplight and you're waiting to cross the street, you want to keep the bike lit up when your wheel's not spinning. So that proved to be a very huge challenge for us. We tried to integrate some battery charging capabilities of this hub generator. So this is just a simplified flow chart, and I'm going to walk you through that process, that design process. But we have the hub generator going through the rectifier, charging rechargeable batteries, which then go through the inverter and the bike frame. So when the wheel's spinning, it's charging the batteries and lighting the frame because they're connected in parallel. And then when the wheel stops spinning, those batteries keep the frame illuminated.
So to observe the behavior of that particular system where you have the charging and discharging at the same time, I set out to observe the rate of discharge of 2 9-volt batteries, which we identified to be good enough to light the frame. So here we see the average rate of discharge as well as an equation that we got to predict the behavior of that system. Also, we observe the rate of charge where you have the batteries connected to the hub generator and allowed to charge over time. We also have an equation of the average as well as the reliability of that equation. So the performance that we observed was that it is expected that the rider speed should be between about 80 to 120 RPM, which would give us an expected voltage output of approximately 8 to 12 volts based on the hub generator testing that we did. Using the battery capacity equation, where capacity is equal to current times time, which basically gives you a predictor of how the batteries would discharge or charge over time. And the current rating of the 0.7 milliamps per square inch over the 140 square inch frame. We observed the rate of charge predicted to be about 40 minutes. However, when we were charging the batteries charged in about 3 minutes, which would give us 97% error. However, it's good that we believe it's good that the batteries are charging really quickly. For the rate of discharge, it was a little bit more as expected between the theory and what we got, in that the predicted discharge was about for 6 hours, but the actual discharge we got to be about 5.018 hours, which gives an error of 15%.
So we were thinking, how can we integrate this battery charging capability into our prototype? So at first we investigated having a double battery charging system because the optimal voltage input for this electroluminescent paint is at least 18 volts. 20 volts is a little bit brighter, but 18 volts is great because you can use two 9-volt rechargeable batteries. So here we put in our circuit, we tried out these capacitors. Instead of one, we had 2 microfarad capacitors, and then they're charging these 2 9-volt batteries. The problem is that this hub generator will peak at 16 volts if you're really lucky, if you're going really fast, but it needs to overcome the 18 volts of those batteries. It's a potential problem. So this system, this hub generator, is not capable of charging 2 9-volt batteries at the same time. So we decided, okay, well, let's try to charge 1 9-volt, which it can, and I'll show you in the next slide. I have a video where this hub generator can charge 1 9-volt, but that 1 9-volt on this paint doesn't light up the paint bright enough. It's barely, on our sample it's pretty bright, but on the bike it's barely visible. So here you see, this is our electroluminescent sample. And you see in the beginning of the video, this battery is about 50% charged. It's a little hard to see, but as the wheel's spinning, so it's a little dim at first, and as the wheel's spinning, you see it gets brighter. And then you'll see when the wheel stops spinning, that it was brighter than before. And we tested with a battery tester that initially it was at 50% charge, and afterwards it was about 80%. So this is video proof that we were able to charge a 1 9-volt battery. But then that still leads to the problem of we need 18 volts. We need at least 16 volts. So we decided to integrate this little DC to DC converter. And what it does is, it's rated for an input voltage range of 3.8 to about 28 volts. So as long as you're in that voltage range, you adjust this potentiometer here, and you adjust it to a constant output. So we set it to, okay, let's have our input voltage at 9 volts, adjust our output voltage to 18 volts, and we did some current draw data, which is on the next slide, but we expect that'll take about 56 milliamps. I'm sorry, 560 milliamps. So when we integrated this into the circuit and we hooked it up to the inverter box, something really unexpected happened. Our input voltage dropped to 3.1 volts and our output voltage dropped to 8.5. And our current spiked to 2 amps. So there's some unexpected interference created between this DC to DC converter and the inverter box. And honestly, the inverter box, it was provided by Darkside Scientific. It's poor quality. Some of the components don't have part numbers. So we really can't analyze what's going on that well in the system. But it didn't work. So we said, okay, let's investigate the current draw of our electroluminescent paint a little bit more. So here you see in orange, this is for the bicycle frame, and we have input voltage and current, and in blue we have for the sample. So with this spec we were given a 0.7 milliamps per square inch. We estimated that we would have a current draw of 98 milliamps for the bike. However, the actual draw is almost 6 times that. We're actually drawing 560 amps at our design voltage of 18 volts. So we're drawing a lot more current than we expected, and we believe that could be a contribution to our problem in integrating these circuits together and having the battery charging capabilities. So we went back to our original design of, let's just light the frame. We want something self-powered. Let's light the frame with just the hub generator alone. So here you see the hub generator spinning in the background and our frame is lit up. The lab is still kind of illuminated because we wanted to show you, you can get an idea of how fast that wheel's spinning. But, so this goes back to, okay, great, we're self-powered, but when we stop our frame, the illumination goes away, which is a problem for us, but we still met our ultimate goal of maintaining a self-generated lighting system.
All right, so the next thing we're going to go over is brake lights and turn signals. The brake lights and turn signal switches were integrated onto the handlebars, strictly basically for ergonomics. And it's very easy. You have one switch, obviously for the right turn, the other switch is for the left turn, and you have the momentary push button switch on the brake lever. So it was a little bit of a challenge that we had 3 switches for 2 light sources. So we were having some current backflow, which I had to put some diodes, and then that solved basically that problem. So this is just a very simplified version of what the circuit actually looks like. There's an inverter box in between there, but this is just to show the difference when I have the 2 switches of when I want one to turn on and when I want the other to turn on. So here you can see when the brake switch is actually pushed on, that both lights will turn on, even if it's flashing or not, or if it's powered or not. If not, it will go through these relays that whether I have my left turn signal on or my right turn signal on, it will power the momentary, the 555 timer, turn on either my right or my left light source. So the brake light, we use a normally closed momentary push button switch. And you'll see in the next slide how this essentially works, but since it's normally closed, that means when the brake lever is not engaged, it's basically pushing down on the switch, which opens the switch. When I pull the brake lever, which disengages the switch and lets it go, it actually closes the switch, which is why the brake lights turn on, because then it closes the loop. So here's just a simple little GIF of how it works with an LED. This is how it was mounted onto the actual brake lever. So we took out the encasement screw, and that's where we put it's just underneath the cable housing for the actual brake. And we put it with a nut so that if it blew out for whatever reason, it was easy to remove and put a new one for maintenance, basically. The next thing we're going to go over is the retroreflective handlebars. So this is actually something that kind of came into play in the middle of our whole design. We initially had wanted to integrate some lights onto the actual handlebars with LEDs, but we realized that we were focusing more on just getting enough power to power the frame. We didn't want to worry too much about the LEDs on the handlebars. So we decided actually to put these 3M retroreflective tape, which you can see this is with flash lighting, without flash lighting. I'm sure all of you have come across this. But this is actually the first of its kind. You'll never see retroreflective handlebars anywhere besides right here, right now. So we really like this because it's very unique about our design. It's obviously absolutely no power consumption. It's just literally the 3M reflective paint on it. So it adds a lot of brightness to it. When the car light flashes over, you might not see the paint as bright, but you'll definitely see those handlebars and they'll flash right at you. And the last thing we're going to go over is system integration assembly, how we put it all together. We obviously wanted to keep this as seamless as possible. We didn't want a bunch of wires all over the bike, making it all complicated, or you getting all tangled up, or zapping yourself. So as you can see from this very simple diagram, we have the switches right here under the handlebars. So it's obviously, again, like I said, ergonomic. They're waterproofed with some heat shrink as well. And these are all routed through the handlebars and then through the stem. And we were not able to drill through the fork because that makes it basically structurally unsound because you have to do a slot since it turns. So after that, we drilled it through the top tube so that we can route it through the top tube and simplify the wiring process here. It comes out here to our encasement, which is on the next slide. So that's going to house our 4 inverter boxes. Okay. That's going to house our 4 inverter boxes and our 6 batteries, and it has notches to keep them all in place. And this is just temporary, but it's going to be mounted right underneath the seat. So it's easily to dismount if you need to replace any of the batteries as well, or the inverter boxes.
So looking forward, we'd like to develop a more cost-effective way of applying the EL paint. Since it was a one-off prototype, our cost to paint was kind of high. But however, you can actually create your own EL paint using materials that can be purchased at companies like DuPont. As Roxana mentioned before, the inverter boxes that we got from Darkside Scientific weren't the best quality. So we can further investigate how to get better quality inverter boxes, as well as investigate a better means of charging and discharging the battery so that the frame can be illuminated even while the bike is stopped. Here we see the timeline, the Gantt chart of our project. So far we're on time, and these are our group members. Some references. Are there any questions?
All right. Perfect timing. Perfect
20
timing.
seconds over.
Perfect timing. I call that perfect. Well, I know my colleague, Dr. Bezos, has been leading this. I was involved with getting the funding for this, but Dr. Bezos was the guy. So go ahead.
Okay, so just one thing that stood out a little bit. So the charging of the battery only took 3 minutes. It seemed.
Yeah,
Okay.
it charges way
That
faster
was-
than you
Okay.
think.
Running at about 100 RPM.
That's just for the Tenergy ones.
Yeah, right.
They had a capacity of what was it, 250.
The Tenergy was 350 milliamp hours.
The voltage out was 10 volt.
Yeah, approximately.
Okay. Interesting. Okay.
We're not sure
Yeah,
why
right.
they would, we were
It-
That seems
surprised.
very fast.
Yeah,
Yeah.
it seemed very fast, but it worked like that for one-on-one,
Okay. All right.
for several trials.
That just stood out, of course. Yeah. But, you know,
Yeah, and a future recommendation would be to develop a more accurate test. Because, you know,
Yeah, right.
we're just
right.
testing with a multimeter how much it's charged, and with that battery tester that has the meter just goes from red to yellow to green.
Yeah. I mean,
And
it's
I'm
not-
sure we could have a more accurate test to
But
really.
still,
Actually, I was
yeah.
checking the voltage over time. So
With, oh, yeah, yeah.
so what I did, I checked the voltage at specific points.
Okay. Yeah, right, right. So I would say it might be worth kind of quantifying a little bit of that. I don't know if you did or not.
Yeah, I
Especially
have.
in that specific spot, you know.
Yeah.
Just
Yeah.
state the two values that you get out and why you think it charged this.
Why you
During
think
that
the charge
3 minute-
faster?
Yeah, that 3 minute time.
Yeah, let me segue out of that too, because I may forget my point on that. It relates to that discussion. What's the RPM for the generator and the crank speed for the pedals?
That's a good question. When you say RPM, like the rated RPM for the generator? Like
No,
how
I think
the
you're
RPM
asking how does it correspond to RPM that you're getting from the hub generator?
With the RPM that is required to charge the battery,
Right.
how it compares with the crank speed of the pedals? What is that? Do you have any measure of that? Like,
we assume to be like the one-to-one.
The idea was, I think you're asking, so how fast can a person actually pedal a wheel, right? I think is what you're asking.
Well, yeah, because
So
the
that's,
crank speed
that's
would be
100 RPM basically, right? So,
Yeah.
and
Between
he
80
he ran the test at 100 RPM. So the charge and discharge were
It
at
should be
that
between
time.
80
Yeah.
and about 120 RPM that you would
Right.
expect a rider to give off.
Right.
so where I'm going, that's a lead-in question to my other question.
Yeah.
Should we have a gearing system for the pedals?
Yeah, well, I mean, this one is a fixed gear specifically to keep it lightweight, and we could probably have it on you don't want to put it on a too easy of a gear because then you're just going to be pedaling out basically and you're going to be exhausted. So you want to kind of find that balance of, you know, not having something that's too hard because you're not going to get that rotation that you want, but not something that's too easy because then you're not going to get anywhere and waste a lot of energy. So,
So conclusion, no gearing?
no, I mean,
If
more
you
than
were-
like,
Gearing
If
doesn't
you
affect
would
the
like-
speed of the front wheel, right? It only affects
No, I know, the
yeah,
pedals.
right. The
Right.
pedals.
It's
Yeah.
I guess depends on the pedalist if
Yeah.
you want
Right.
to make it easy on themselves.
But then the application of all of that doesn't depend on a geared bike or not. In fact, it would work for any bike.
Mhm.
It
And
just
this is-
depends
we
on
did it
comfort.
strictly, yeah, we did
Yeah,
it
it's just
strictly on a fixed gear for the
Yeah.
simplicity of it, that we didn't want to, you know, that wasn't the emphasis of our, we were focusing more on the actual illumination of the bike, so we don't want to worry too much about the gearing of it, that we just, because you can always switch out your fixed gear as well. If I want something that's easy, you just replace the cog on the back and we got the gear on the front, so. That's what's great about fixed bikes. Very
Okay.
easy to take apart.
Retrofit, yeah. All
And
right.
this is just like one initial prototype. To make something like this marketable, we would need to do multiple prototype iterations, and that would actually be a great thing to test
Right, with
in
gearing,
the
yeah.
future.
All right,
So some other just presentation comments. So, and then on your circuit diagrams, if we can go back to those.
Yeah.
Just if you can, keep going, keep going.
The brake ones, the brake switches.
Yeah.
This one.
Yeah, sure. Yeah, same thing. So
Yeah.
just It's okay if you have the whole diagram there. It's better to have the whole diagram there. But when you're identifying the couple nice things, so it might be worth if you can just show open and then the pathway and then close and a pathway if you could. Just draw it on there.
A
With
different color maybe.
Well, that's
Right,
why
or
the
something.
green shows that the current, when this one's closed,
Right,
goes
right.
to this one,
Okay.
and this one's open, so the current goes to the
Perfect.
switches.
Okay. So
just put the
it's just
label
very hard to.
I just put the label in.
Okay. Yeah, that's fine. So just put a nice big thing so that we see that, and then you can see exactly where we go.
Mhm.
Okay. I know I have some.
Well, let me tell you about that. Go to the mainframe lighting,
The circuit diagram?
Which one?
mainframe lighting slide.
Yeah, just keep going back.
A few slides.
Yeah, it's way better.
It'll be the next circuit diagram. This one?
Yeah.
Yeah.
Those numbers, could you do something to?
Yes,
make-
actually, I realized today, right before, that I'm gonna add a table where I have the item number and, yeah.
If you can put them right next to the numbers,
yeah.
create a table, yeah.
Yeah.
Okay. All right, so that's one point.
And I know.
So,
Oh, sorry. Just I know. You did a pretty good. You all did a good job of explaining each component. You took your time with it, but it might be worth discussing what you said. Bridge rectifier, what it does. You said capacitor. Just be careful when you're actually giving the talk, because sometimes you talk quickly. If you're relying on yourself to say it, sometimes you skip over it and then people get lost. So worst case scenario might be worth a little thing in the corner. Capacitor is this symbol, bridge rectifier is this
Yeah.
symbol, or something like that.
Yeah.
Just so that you,
a little legend.
worst case scenario, you're
Right.
running pretty quickly or
Sure.
something.
Nice little legend. Yeah.
Right.
Go to your performance slide for me, please.
Oh, this one?
Yeah. Let's see
We were shocked at it.
Yeah.
We,
The true
Remember when I
max,
first tested it, I was like, I
Yeah.
swear, just like 3 minutes.
Yeah, it was very interesting.
Not actually measuring it, just like
Yeah, right.
real
Yeah.
quick to tell you, and I got so excited.
here. Okay, I think you went by that too fast for me, so I'm happy with that. And then the other thing is, that polling apparatus you have on the back, it almost seems to me that if you're riding in wet weather, it needs some protection, so you probably need a fender, don't you think? To keep it from splashing?
Well, actually, I have a printout of half of our actual encasement.
You mean the one that we're 3D printing? Or this
Oh,
guy?
this is just temporary.
That's why
Yeah,
this is what we're actually doing. So the only thing that's
That's
gonna be
not-
exposed on the bottom are these holes, and we're probably gonna be putting silicone/heat shrinking, so there's not gonna be any water getting in there.
Okay,
Yeah.
all right.
Yeah, we're taking everything we took into consideration. If you got caught in the rain, I don't wanna get zapped kind of thing.
Okay.
Yeah, and
So,
the other half is
Did you
printing.
say that in the presentation?
Well, I said that actually more with the switches, because that was our initial concern,
Yeah,
obviously,
but-
before
but
the encasement, but
All
yes.
weather riding could be an issue, so address that.
Yeah, no, that was also our main concern that we've been keeping into consideration,
Okay,
so.
all right. The other thing is, are you fully aware of the rubric on which you would be evaluated?
Yes.
Okay, so bear that in mind, and I didn't see any problem with units, which is another one of my pet peeve, making sure that we're talking to all the different audience when we make reference to units. So bear that in mind if in fact I did miss it. I have nothing else.
I'm good.
All right, very good job.